Hey there.
Well, hi Mike, how you doing?
Really good.
Hey, I appreciate you doing this discussion after last week's talk. Obviously, it fits right in with where I've been thinking.
Oh, okay, cool.
Oh, yeah.
Yeah,
So,
the next one I'm going to do is on all the different audio inputs. Looking at the phono versus auxiliary and why they're different and stuff like that.
okay,
I'll go into the RIAA equalization and all that sort of stuff. And it
okay,
kind of ties with what we're doing today too.
okay, okay. Well, I've been pondering just a little bit with these old Atwater Kents what the impact of replacement transformers is for the interstage stuff. And so being able to sweep the frequency and take a look at uh, that world a little bit is where my interest has been recently.
Right, right. Yeah, this fits right into that. And as we'll talk, just using a simple square wave is a great way to do that.
Yeah,
Have
I
you done
think
that before?
I have. I have. And we used to use it quite a bit in other higher frequency stuff that I in my earlier career. Not
Right.
not radio waves particularly, but certainly higher uh, uh, ultrasonic stuff, that sort of thing. Yeah.
Well, you can probably do a lot to correct everything that I say and help add more content then. That'll be great.
Well, no, and of course, I my special interests don't won't mean much to anybody else because they they hardly mean anything anymore to technology anyway.
Yeah.
uh,
I find it funny, especially with like you do the same thing I do. You get into some little esoteric thing and then you just drill down and you till you hit water.
yeah,
Uh,
yeah, yeah,
and
that's
then
me.
keep going.
That's me. And of course, part of this is a history lesson. As you know, I like Atwater Kents, and what I love about them the most is they represent the very beginning of the radio industry up until the mid 30s when it's pretty stable.
Right.
And you kind of see each step. You can almost see the engineers' minds working as you kind of go from unit to unit.
Yeah, that is true. I mean, I have found all of that exact same thing fascinating. Um, I look back at I just recently picked up a, wire recorder and I had one as a kid and I didn't, I really enjoyed playing with it, but I didn't realize how much of an important step that was, and I think all of these things are an incremental step to get where we are today.
Absolutely,
And you probably couldn't take one of those out um, and still be where we are today. It took all of those
it did.
pieces.
It did. Yeah, pretty interesting stuff.
Yep. Hey, Jake,
Hi, how's it going?
really good.
Good.
Hey, Myron, sorry I missed you. I couldn't make it to the meeting, so you still don't get your steam engine.
We'll get together eventually.
Someday.
Yeah.
Well, I sure wanted to get to the Dick Del Schneider service. Uh, we had my brother-in-law had passed, and his service, his graveside service, was Friday in Spokane, and we didn't get back in time to get into Saturday's event. But how did it go?
I was only there in the early morning to help set up, and then I had to leave, so I wasn't able to stay.
Okay.
Anybody else went to the memorial service and the auction afterwards?
Yeah, I was there. It was very nice. We were upstairs and a number of people spoke about their experiences with Dick, and there was some cute moments and
Hmm.
and some, nostalgic moments and that was pretty good. And then we went downstairs and there was food served and everything was set up with Dick's radios were in the middle row of tables.
Hmm.
chairs on either side, and then the other auction things were on the outside tables. Um, we did the radios. We did Dick radios. We auctioned Dick's radios first, and I think it went really well. I was surprised because I was expecting the club is so cheap, and those
Yeah, that
reserves.
some of the reserves would just not be met.
Yeah, so we sold everything except for two radios. One of them was that really nice Zenith console. It had a
Hmm.
reserve of 300 on it. That didn't sell. And then there was a 41 Philco, which they advertise as a log cabin. It's one of those desk kind of
Yeah.
radios.
Hmm.
That had a reserve of 100 on it, and nobody went for that. But everything else sold. There was a guy whose name I'm not familiar with from has a shop or a store on the east side. I don't really know the details, but he's bought from us before, and he bought a few things like there was a Zenith neon sign, which we didn't have there, but was in the pictures,
Hmm.
and he bought that for pretty good money. And there was a surprise in some of the test equipment. There was an stereo audio analyzer piece of test equipment I've never seen before. I think that thing got bid up to like 300, more than $300, So
Huh.
that was like the first thing out of that group that we sold, and it just kept going.
Who bought that? Because I was interested in that, but I was really surprised it
It
went so
might have
high.
been the guy that I was talking about, who has the shop. It
That's
might have been him.
Brian Schnatter.
Good. I'm glad you know about this,
Yeah, that's
Pat.
Brian Schnatter. I think the top price for that was 200. I don't think it was three. I think it was two.
Oh, okay, okay. But I was just surprised that it went so high because nothing else on that table went for anything like that.
Well, it was also, no guarantee to work. I mean, it was just there as is.
Yeah, everything was. But I guess, in general, I thought that certainly Dick's stuff, I was really surprised at meeting the reserves on those. And there was spirited bids on a few items, but everything, met the reserve, and I was pleasantly surprised. So it was a good day.
Nice. That's good.
Well, are you ready for me?
Yeah. Yep. Whenever you're ready.
Let's see. Oops. So what I thought I'd talk about tonight is how to do some audio amplifier testing. And to do that, we need to really talk about what frequency response is, what distortion is, and then we can get on into some different ways of testing it. So frequency response and distortion. So frequency response really, I mean, if we think about what an amplifier is, the goal is to take a really small signal and increase it to a larger signal, to amplify it. But the output should not change. So whatever we put into the input, it should be the exact same thing on the output, only bigger, louder, more gain. Distortion relates to the fact that if you put something in on the input, um, an expected input, and then the output is different from the input. That can be considered distortion. Sometimes distortion is desirable. I mean, tone controls, RIA equalization, all of that stuff. That is you can kind of think of it as a form of distortion because it's actually, changing what the input is. And then frequency response is the ability to amplify all of the frequencies in the desired spectrum. So if we look at the picture down here below, the human hearing, unless you've got gray hair, is somewhere between 20 hertz and 20 kilohertz. As you get older, that drops off, or if you're married, that drops off, those kind of things. But in general, they think of the audio frequency somewhere between 20 to 20K. And so ideally, you would like any amplifier, if you put in a frequency between 20 and 20K, you would, if you put in a 0 dB frequency, you would really like it to not attenuate at all. You'd like that attenuation to be zero. And so whatever volume, you can kind of think of it that way, whatever volume you put in, that's the kind of volume you want to get out after the amplification. So the bandwidth is making sure that the amplifier will handle low frequencies and high frequencies equally. We talk about attenuation, and that can be, a positive dB or a negative dB, but that refers to reduction or an increased value. Any questions, comments, or corrections before I go on next?
Remembering that dB is a ratio, right?
Oh, yes, and that's a great point. So the dB we're talking about is, let's see, we're talking about dBm, I believe, and it's going to be, dB is always a ratio. It's whatever the output over the input, or some different form of a ratio. It's not a specific number. So let's talk about what distortion is. We mentioned things like tone controls and stuff like that can actually affect it. There's a lot of different kinds of distortion, and I'm only going to mention a few of them here. And for the true audio people, they probably know this stuff inside out and much better than I will ever be able to understand. But one big one is harmonic distortion. And the problem is anytime you create an oscillator or there's a sine wave, unfortunately, harmonics or multiples of that, what we call the fundamental frequency, will be created. So if you have a 1 kilohertz signal, 1,000 hertz, well, you could get a 2,000, a 3,000, a 4,000, and it'll be an even multiple of that fundamental frequency, whatever the initial frequency is. And I believe you can also get harmonics on the downward side too. Intermodulation distortion, it's not really harmonics. It's an interaction between different frequencies. It's kind of like throwing the pebble in the water, right? How the waves get generated, and you throw another pebble in, and then those waves can mix and match. And so they talk about intermodulation is when frequencies start interacting with each other, and you can actually kind of think of that as what we talk about in the AM radio spectrum, right, where we have our mixer, and we're putting in the IF frequency, we're putting in the RF frequency, and then we're going to get different frequencies out. You're going to get the main frequencies that were put in. You're going to get the addition of those as well as the subtraction of those. And those are called intermodular or intermodulation distortion. Clipping, that usually refers to the fact that if we think about like a sine wave, when we start cutting the tops or the bottoms off of the sine wave, and we'll talk about more about how that can create other types of distortion, but that usually happens like when you there's a couple ways it could happen, but one of them is like if you overdrive your amplifier. So you're putting in so much signal on the input, it's trying to do the appropriate amplification, say 100 times or whatever, but your output tubes or transistors or whatever can't go any higher. It can't actually reach that, and so it just hits the maximum and then just flattens out. So that's what happens. That's clipping. That's another type of thing that can create distortion. Amplitude distortion is along the same lines of clipping, and a lot of times you might have, if we think about an alternating waveform, kind of like down here, we always think of the zero line being at the center and it'll go above and below zero. Well, if you create a DC bias or you raise that 0 point, you add some DC to it, what happens is this whole waveform moves up, and the next thing you know, you can start clipping just on the peaks, or if it goes down, you'll be clipping on these dips. And so the amplitude distortion, when it'll start affecting it, is an example. Quantization, that usually relates to digital processing, because the way the digital processor works, it's going to take the analog waveform and it's going to do what's called sampling. And it's going to walk through and it's going to say, like on this waveform here, it's going to take a sample here and here, it's going to take all these samples, and it's going to figure out what the digital value of the amplification is, and it puts all of those together in as data, and then that data can then be converted back to analog later after it does things. Well, the problem is if you don't have enough depth of your capture signal, or you don't have enough samples, you can actually lose a lot of information, because if I was doing a sample like every quarter, I might get one here, I might get one here, I might get one down here, but I wouldn't know about all of this signal in here. And so the quantization relates to just having not enough sample rate to be able to accurately represent the data that you're looking at. And I think there's some Nyquist stuff that you can look at to determine, what the maximum sample rate you can have to make sure it's got to be like double whatever your frequency is or something like that. Phase distortion, that happens when if you have two signals. If we think about it like a left and a right channel is probably the best way to think of phase distortion. And a lot of times what's going to happen inside of a radio is you're going to have separate electronic components amplifying the left channel and the right channel. Well, if you have some, and in theory, what's going to happen is they're going to come in phase. It's going to walk through the circuit, do its amplification. Then when it outputs, they're still going to be right in phase. But if you've got some problems with, say, some additional inductance or capacitance on one of the sides of the left channel or the right channel, what's going to happen is it may shift the signal a little bit on one of them, but not the other one. And so now you're going to have a phase distortion, because when it comes out, your left and right channel may not be exactly in line like you think. And that can be a problem. Another example, simple example of this is when you have two channels of speakers. The speakers have a red and a black, right? A positive and a negative. And in most stereo amplifiers, the amplifier is not going to go from ground to a positive level. It could actually go, positive and then go negative. Well, if you have one of your speakers connected reversed to where, let's say the positive is going to be pushing the cone of the speaker out and the negative is going to be pulling it in. Well, if you have another speaker that's doing the same thing, but you've reversed the signal, what's going to happen is when the one speaker is pushing the cone out, the other speaker is pulling it in. And that, is going to end up canceling each other. So if you were to put the two speakers and push them next to each other, in theory, you would see a much quieter signal. Or if you put them in phase, it could actually sound louder because it'll be amplifying it. And so that's where phase distortion comes in. Typically, it relates to reactive components like capacitors, inductors, that are either going to slow down, speed up, or shift the phase of the signal going through till it gets to the speaker. And then crossover distortion. This happens a lot in the we're talking about a lot of tube related stuff, but in the more modern amplifiers, what they have is that they're going to have, and even in pretty much any push pull, you're going to have a situation to where, say you've got two transistors, and they'll put like a PNP and an NPN, and they'll put them basically to where you've got we'll call it a 20-volt signal on the top of one of them, negative 20 volts on the other one, and then they're connected in series, and the center between them is going to be your output, and it's going to determine is it sending the 20 volts here, is it sending the one here. Well, the problem you have is when this transistor turns off and this one turns on, they don't exactly turn on and off at the exact same time. And so you're going to get this crossover distortion where the one transistor is getting close to zero. You know, if you remember like a diode, right? The diode will turn on at 0.6 volts, right? So there's that time between 0 and 0.6 volts where it doesn't turn on. And then when it's turning off, you know, if you start having 1 volt, you know, 0.5 volts, once you hit that 0.6 volts, well, then it's going to shut off. And so you don't actually have linear movement between, say, that 0.6 volts and 0. And that happens with the transistors too. As the input moves, you're going to get this little area here, what they call crossover distortion, where you run into this problem. Now you can do things like biases and things like that to improve that, but you do have to be careful of this because this is going to affect that signal also. Any questions, comments, or other types of distortions you want to talk about? Do you have a favorite distortion? Okay, we'll move on.
I've got a question.
Sure.
Christian Winfield, does the guitars and amps, and he says he's always looking for bad capacitors to put into these amps because it gives them the sound they want to hear. What does it do when he puts bad capacitors in his guitar amps?
So we actually discussed this a little bit on the last presentation. John was talking about that, I believe, with the radios that he works on, right, John? I think you're muted. There you go.
There we go. Yeah, I've used, but certainly there are bad capacitors. But in this particular case, Outwater Kent actually made what we would consider today a faulty capacitor, one that had a power factor of about 40%, and it was designed into it for a very specific reason.
And so basically what it does is what Christian might be wanting to do, it depends. They have those things like the fuzz pedals and stuff like that, and that's introducing distortion. Sometimes this gets really complicated because, especially when you're talking about audiophiles and stuff like that, that's a whole nother class of people. I mean, they're just very unique in themselves, and it gets into what they can hear and how it sounds. And sometimes if you've got like a leaky capacitor, it will actually make the sound different. And some people think it sounds better. Some people may think it sounds worse. It might give it a warmer, smoother sound to it because it's leaking. What is it doing? That's a great question. And trust me, there's a lot of people have tried to figure this stuff out. And to my knowledge, I don't know if there's an answer. Some people have a lot of speculation, but I don't think it's well defined. But some of it could be that, it just kind of, when the input waveform comes in, it's changing it just enough to where it sounds a little bit different. And some of that could be the changing the bias a little bit. It could be adding a little bit of phase distortion. It could be a lot of different things that it's affecting. I honestly don't know, and I'm not sure if anyone actually knows what it is, because there's a lot of debate about this online.
Okay, sorry, I didn't mean it, if we've covered it before, if it's, strange. I just
Oh
look
no,
at
no, no.
that.
It's not that we covered it before. It was just John mentioned the same thing in the Atwater Kents last time. But it's a great question.
Well, if you have a capacitor like the little bumblebee things and you have a radio that blows up, it doesn't work. So when you have a capacitor that's going bad and you stick it into an amp to get the certain sound, what's the guarantee that's going to last? I mean, it died basically, and something happened to it. But if you put it in a circuit, expecting it to perform like that, I mean, the insides could be half burnt out. I mean, who's to say that's not going to last a minute or a day? So I don't quite understand
Oh
doing
no,
it.
no. I think you're right on target. Personally, I would never do that, even because like you say, if you've got a capacitor going bad, um, it's probably going to keep getting worse. And so it's not something I would want to put in a circuit. But if it was intentionally made that way, or, if you wanted to try to simulate it by maybe putting a resistor to simulate leakage or something like that. Um, but yeah, they have found that some capacitors sound better than others. And that, some of that is, very non-deterministic. It's purely by ear. But yeah, I don't know as I'd be putting bad capacitors in, um, because it's there. I don't know how you would quantify something like that. Anybody else want to comment on that?
The only thing I might add to that is for sure you would have the opportunity, a one time opportunity to say, I like this sound better or I don't. And most likely it would take away some of the harshness that we sometimes hear that comes through. Um, but would it stay stable? It's usually you start seeing capacitors fail because of moisture contamination into them. And would that eventually stop? Would it stabilize at some point? I'd be really surprised. So, Pat, to your point, would they be stable 10 years from now? Would they get the same sound? It's hard to believe they would be that stable.
Right. Yeah. Not only that, when you're talking about especially older capacitors like the bumblebees and stuff, um, they're probably going to keep deteriorating. I just don't think that they're gonna stabilize. I just would find that hard to believe. And I think you also have to be very careful where you're putting them. He's not going to be putting them on the power supply more than likely. He's going to be these are going to be like bypass caps and things like um, that are feeding the signal through, and he wants to generate a little extra leakage or something. Would be my guess. John, where is that one that you found that the Atwater Kents used? Was that a grid bypass type cap?
What it was on it uses a set of 45 tubes in a push pull configuration. And this quality capacitor, they call it, quality device, which they, by the way, never give you a size of. You don't know. In fact, that's why there's great debate online is what should we replace it with? But it is right directly across the two plates.
Uh,
So it's in a bizarre spot. You don't see those types of capacitors, or you don't see capacitors across the plates like that very often. And by having a high power factor, it's the equivalent of having a resistor in series with them. But it's not just a normal resistor. It can't be duplicated with standard resistors because the way capacitors work, it's a really weird theory, but it turns out it becomes frequency dependent and not
exactly.
standard capacitive. It doesn't follow the capacitive curve for frequency. It follows its own curve, and so it ends up shaping the bandpass of the entire device in a very specific way, yeah, this curve, it affects that curve pretty dramatically in a way that I can't figure out how to reproduce with modern components.
Yeah, so to just reiterate what John was saying and back up just a little bit to make things, because when we start talking about capacitors and things like that, we talk about reactance, and we think of it sometimes as resistance, but we have to remember that true resistance, what we're talking about resistance, we're talking about a DC level, and the nice thing about DC resistance is it's consistent over a frequency range. So, if I put 5 volts in with an AC signal across a resistor, I can, if it's 5 volts RMS, I can go ahead and calculate what the voltage drop is. And if I change that frequency from 60 hertz to 1,000 hertz to 10,000 hertz, if it's 5 volts equivalent RMS, I'm going to have essentially the same voltage drop across a standard resistor. But when you start talking about capacitors and reactants and things like this, and inductors, exactly as John mentioned, um, the AC resistance, how that component resists AC varies with frequency. And so there is not a single resistance, quote, resistance value, or a reactance value to a capacitor, because as the frequency changes, that reactance or equivalent resistance is going to change. And so this is where they take advantage of this in the audio spectrum by having different reactants. You can actually get different functionality at the low end versus the high end versus the medium area. So yeah, it gets really, really complicated, and being able to reproduce that stuff would be really, really hard. Probably take years of simulations in hope of maybe doing it. And it wouldn't surprise me if a lot of the people just figured it out by experimentation more than anything. Myron, you had something to say, or?
Well, there was one thing I wanted to comment on. I'm not sure if many people are aware of almost always in the output section of a radio, you'll see a capacitor across the output plate where it goes to the output transformer. And the purpose of that capacitor is to keep from killing the output transformer. And it's, sometimes more recently been called a snubber, because what can happen is you can get a really high frequency spike on the output, typically on AM from like a lightning hit or something like that. And so when you get a really fast rise time signal, then the inductance inside the output transformer can produce a high voltage, and it'll short out the output transformer, burn it up. And so that's the purpose of those capacitors that are always, I say invariably, it's on the plate to ground or it's across the output transformer in the audio section of a radio. And
If someone wants to pull up a schematic of that, we'll be glad to share that.
It took me a long time to understand what that was about. I thought they were just trying to keep high frequency, kind of roll off the output so it doesn't sound bad. But in fact, it's to keep from killing the output transformers. Now, in the case of an Atwater kit, they may not have very much of an output transformer because they're driving a high impedance speaker, right? So
we're talking about the 45 or the 55. So now we're talking about the voice coil speaker.
yeah, so it has an output transformer.
It does.
And then you need a snubber there to keep from killing the output transformer.
And
it people don't understand that, I guess is what I'm trying to say.
It does do that, but it also does influence the bandpass. So it also
I think it's doing dual duty there.
There is another comment. If you ever get to that, we can have a little conversation. There is a particular type of capacitor to consider in those cases. As you suggest, what happens in a lightning strike is the tube immediately shuts off. And when it does, if the if it was conducting hard, that inductance on that output transformer, just like you said, is high enough that it'll produce high voltages. And the snubber does resolve a lot of that problem, but there are better choices for capacitors. And at some point in time, I'll try and pull out the information on that when you pick and choose to deal with those.
I love this group. I learned so much, just everyone has great input. Thank you. Okay, so part of the question comes in, well, how, there's this thing called a distortion analyzer, and how does that work? And if I've got an amplifier and I want to measure my distortion, what do I do? Well, distortion analyzers are really expensive, and the way they work is they'll interject a fundamental frequency, say like right here. They'll interject a frequency, and then what they're going to do is they're going to look at the output, and they're going to create a notch filter to get rid of that frequency. So this fundamental frequency goes into the input, and then they on the output, what they do is they look and see, since I'm only putting in a single, just one particular frequency, say 1 kilohertz, I shouldn't see anything else, right? Because a perfect amplifier is going to amplify that one frequency, and I won't see anything else. But what they look for is, are there other signals that are showing up, like here, 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 here? And they're going, oh, okay, well, I put this frequency in, but look at all these other frequencies I get. And so this is one way that they do distortion analysis, is they'll look at it, and then they'll find all the other ones. And then they can notch filter this one out, figure out what this is, and then come up with a number and tell you, here's how much distortion you have based on our input one. And ideally, it should show like 0, right? Because if you put just a single frequency in, you're not going to get anything else out. But what they're doing is they're trying to find all the unwanted frequencies that may appear either through harmonics, typically harmonics, but or other things that could happen. So the question comes in, well, how do we do that? Ideally we would like to test an amplifier by testing every frequency, so we could put in every frequency we could think of within the band limit and make sure that it's not attenuating. In other words, we don't want it to be reducing or even increasing the amplitude. And we want to make sure that there's no more unwanted frequencies. So we want to put a frequency in, check it, and then we want to go put another frequency in, maybe at a higher frequency, and start at 20 hertz and go up to 20 kilohertz. And every time we put one in, we really want to make sure that if we put in a particular output amplitude, we want that or input amplitude, we want the output amplitude to be the same no matter what frequency it is. And this is called sweeping, and this is what a sweep generator does. In fact, we were talking about that one piece of equipment that sold for so much at the auction. Well, that was a sweep generator. And what it can do is you can tell it, I want to not just put one frequency in like a normal signal generator does. I want to put in a whole spectrum of signals. So I could put in, I want the signal generator, the sweep generator, I want it to sweep between 20 hertz and 20 kilohertz. And I want you to take, say 3 seconds to do that sweep. So in 3 seconds, it's going to do that whole sweep for you. And then you can look on an oscilloscope and you can watch as it sweeps and see if your signal gets higher or lower. And you can kind of tell, if it's if you've got a nice waveform, you'll be able to tell if you're getting extra waveforms or not. But sweep generators can be expensive, I guess, especially if you try to get one at the auction. Not everyone has access to it. And it can also be difficult to analyze unless you have a spectrum analyzer, which what a spectrum analyzer is, that's kind of what this is. If we think of an oscilloscope, this top part here is an oscilloscope. So this is amplitude versus time. And so, as time goes on, we see the amplitude change, and that we know of as a sine wave. A spectrum analyzer does something different. It's not like an oscilloscope where it's measuring time on the horizontal axis. Instead, the horizontal axis is frequency. And in the vertical axis is typically a form of amplitude or dB change or something like that, dBV. So what you're looking at here is actually the frequency. And so, if we change the frequency, we would expect to see all of the frequencies that it found in here and what their amplitudes are. So how can you or I do it if we don't have a spectrum analyzer? So before I can answer that, we need to kind of go understand waveforms just a little bit. I promise it won't be too detailed, but it is important to understand because there's some sneaky things we can do. So a sine wave is the purest of all signals. It's a sine wave is, if we look at this one, what we're calling our fundamental frequency that we looked at on that previous one, that's just one frequency and only one frequency. And that's really nice. That's really clean. The problem is audio frequencies, audio signals are a combination of a whole bunch of sine waves. And Fourier figured out that you can actually dissect audio or any waveform into its fundamental parts, which are a whole bunch of sine waves. Now, one cool thing we know about these harmonics, our harmonic is a multiple of a fundamental frequency, 2x, 3x, 4x, 5x. Well, the interesting thing is a square wave combines an infinite number of odd harmonics. And so a square wave, if we look here, what we've got is if we have our fundamental frequency, we have the third harmonic, we have the fifth harmonic, and if we keep going and going and going and put all those together, our result is actually going to be a square wave. And so a square wave is not the absence of anything, it's actually the presence of all of the odd harmonics. So if we think about that, well, if a square wave actually is all of these harmonics, so we have lots of different ones. I mean, we don't have the times 2 and the times 4 and the times 6, but we have a good spectrum of frequencies that can go a long way. This is really nice because we can almost treat this like a sweep generator. All we have to do is put a square wave in, and we kind of built our own sweep generator, which is really cool. So we can put a single frequency square wave in, and really what we're doing is we're putting in lots of these, and we can actually test for that. I think that's really cool. Hopefully other people do too. Otherwise, this will be a real boring presentation. So
that is really cool.
great. See, I'm not the only one.
It's interesting.
I'm not the only weird person here. So
The one other thing is that the harmonics go down as you show in the
Mhm.
diagram
Yes,
there.
yeah,
The amplitude is
the-
successively less.
yes. And that's good to understand that the amplitude does go down. Thank you. So one of the cool things you can do now that we've got our poor man's sweep generator here, a simple thing that we can do is we can put a square wave into the input of a amplifier, and we can look at the output. Now, let's think about what the goal of an amplifier is, right? An amplifier, whatever the input is, it should look the same when it comes out. Well, if we don't get the same kind of square wave coming off, then we know something's happening to the frequencies. It might be this frequencies here. It could be the ones over here. We don't really know which ones per se, but we can get a good guess. We don't know exactly what they are. So if you start seeing your square wave tilting down like this, that means we're going to have some low frequency roll off. So that means that the lower frequencies aren't doing as well. They're getting attenuated when we really didn't want them to. If we got high frequency roll off, the front of the curve is going to look like this. And so that's not good. Here's an example of some severe low frequency. This would be, like you have no bass and you're all treble, right? You're going to get something like this. And by the way, if you want to test your treble and your bass on an amplifier, go ahead and put a square wave in. And as you adjust your tone controls, you're actually going to see your output waveforms do this on an oscilloscope, which is really cool. Here's a case of what they call ringing, and that indicates certain problems within. I'm not going to go through how to fix all of these things, but it will help you identify it. You might always get a little bit of ringing, but if you get quite a bit of ringing on here, then that's going to give you a hint that there's something going on. This one's saying you've got narrow bandwidth, which means I would guess that you're probably losing lows and highs. So you're down to, you've got maybe only some mid-range going on. So you've got some additional problems. And then here's like a composite diagram I found that shows you all the different kinds of things that you could see. Here's where you boost your trebles. So, instead of getting your square wave you're expecting here, all of a sudden now we're boosting our treble. And then here's where the treble gets cut. Here's where the bass is being boosted. So we're pushing it up here. And then here where the bass is getting cut. Treble and bass boost, obviously it's going to look something like this. So your mid ranges are going to stay a little bit lower. Treble and bass cut, you're going to be lowering each one. A band pass, that means that you're actually boosting the mid range. So here's what you would expect on the 1 volt here for the, this is what you would expect to see, but we're boosting the mid range. And if you remember, like the old component stereos where you'd have the big equalizer with all of the different knobs on it, and you probably always wondered what you were doing. Well, that's actually giving you more than, like, when you say treble and bass, you're really talking about like the low end or the high end. But what if you wanted to manipulate every little bit of this waveform? With the equalizer, you could go say, I want to increase the treble a little bit. I want to lower the bass a little bit. I want my mid-range higher, but it's not just the mid-range. Maybe you can have, 7 or 8 steps in here that you can control. And that's kind of like what an equalizer does. And in here, instead of a band pass, we're going to actually be attenuating the mid-range. So we're going to attenuate the mid-range, and this might actually be boosting the treble a little bit here too. So you can play some games just by putting a nice clean square wave in, and then looking at the output can give you some hints on what's going on. Now, is this cool or what? The one other thing I wanted to mention, we talked about this, and I wanted to talk about clipping a little bit. So on more of the modern stereos, less so on the stuff we have, because if you're looking at the vintage radios, I think we almost usually always have like an output transformer, and so you're not going to have the same kind of thing. But in a lot of the transistor amplifiers, the transistors are driving directly, and that's where you start getting that crossover problem and stuff like that. But you can end up with a DC bias, and that's where on modern amplifiers, you always want to check your left and right outputs, measuring the DC output with no noise going in. So you turn your volume down, you just measure the DC output on your speaker connectors. And if you've got a positive output, anything more than, they say, you'd like to be even well under 75 millivolts, maybe closer to like 50 millivolts or less. Ideally, 0 is great, but not always practical. What happens is it shifts this input signal up. Well, when you shift it up, we talked about that before, right? That's that amplitude distortion. What happens is you end up start clipping up here. Well, you remember how I said that the sine wave is the purest wave? It's just like a single output, right? There's no theoretical harmonics associated with it. And you remember how I said a square wave is a whole bunch of odd harmonics? Well, think about what happens when you start clipping. The minute you clip, you just created essentially like a square wave. And depending on where the clipping is happening, that could actually generate additional harmonics that might continue on down. So if you're clipping at your preamp or something like that, you're going to end up passing a essentially kind of an ugly looking square wave through the rest of your system, and that could induce a whole bunch of odd harmonics and then create even more distortion. The last thing I wanted to really do was just mention a warning. If you're working on stereo amplifiers, not necessarily the stuff we do with the vintage radio, but if you're working on any of those at all, be really, really careful connecting your scope to the ground connection. Because not all, I'm not sure, maybe you guys can tell me if it does happen in the vintage radio stuff, but I know in the other ones, there are amplifiers out there to where the on the RCA jacks, that ground connection is isolated. In other words, the left and the right ground are not the same. And so if you connect your scope to it, you can actually blow things up. So you want to, before you do any scope connections or anything, make sure that the ground part of your speaker connection is actually negative. It's earth ground, not it's not connected to a floating negative. That's pretty much all I have. I have some additional things here on the slides if you guys want to click into it. There's some really excellent articles that will tell you a lot more about all this stuff than I ever could. But that's all I have. Hopefully that was useful to people.
Yeah. Yeah, thanks, Mike.
But it's a real simple way to take a look at your amplifier to see if something weird's going on.
Mm-hmm.
Does anyone have a schematic they want to pull up that shows that snubber?
I can grab one.
I was just going to briefly mention that what Fourier figured out was that any arbitrary waveform can be created by adding up the correct number of perfect sine waves of different frequencies. You just add them together. So any arbitrary complex waveform can be broken down into a sum of sine waves.
Exactly. And then you'll notice on some oscilloscopes, they'll have what they call an FFT.
Yep.
That stands for fast Fourier transform. And what it does is it's doing those transforms. It's breaking down that arbitrary waveform, whatever you passed into it. It's going to take that and break it down into the individual fundamental frequencies the best it can. And it makes it look essentially like a spectrum analyzer.
Yep.
Just as a comment, this is the Atwater Kent circuit that I was talking about. Here is that what we were referring to as a snubber, but you see the push-pull amplifier going into the output transformer. This one goes directly across. Usually you see the snubbers either located on the input side so they don't have to handle quite so much power, or they're located from here to ground on one side of the to keep the. But what happens in the early stages, if a lightning bolt came through, it can shut off that tube in a heartbeat, and it was a completely open circuit, if you will. If there was current going through the coil at the time, and there would be, it produces a very high spike voltage, and this would absorb that. But this particular device, if you ever look for an Atwater Kent model 55 or 60, you'll be hard pressed to find any publication that'll tell you what is that capacitor. What if I want to replace all the capacitors in a rig, which I don't normally or don't always, but that's one you never know what to replace it with. And that's where the conversation got started. That's the device that, as it came from the factory, I've pulled out about 4 of these now, and they're all very, very close to the same value. This is that one that has a very high power factor. And it does really interesting things as a tone control for this particular device.
Yeah, and back to the snubber, I just want to mention, the action there that happens is exactly what happens in a Kettering ignition in an automotive
Yes.
application, right?
So I just pulled up a schematic. Is that this capacitor here?
Yes. Why does it say it has 2 different values? Oh, does it say C15? I thought it said 0.015. Yeah, no, it's C15.
It's a 0.03.
Yeah,
0.03.
yeah.
Yeah.
Gotcha.
You see anything from there up to a 0.1? The other interesting thing about this particular set is that tap on the B plus there is to eliminate residual hum in the output.
Yep.
That's why you have an extra wire on the output transformer.
It escapes me. What do they call that?
I don't know what it's called. This is a Zenith, right?
It's the equivalent of humbucking.
Oh, it's a console tone. Yeah, but Zenith used it starting in the early 40s. They just added, so it's equivalent to the humbucking, as
Yeah.
Cliff says. Yeah. You see some notes in the Zenith. Oh, it is a Zenith. Okay.
Yeah.
You see some notes in the Zenith literature that says this is a new thing and you should understand it. But there's like some notes in it about the extra wire in the output transformer, basically.
And if I remember right, it's because of the way they tied this, keeping the red line as your common. This section is out of phase, right, from this.
Yes,
so-
exactly. Exactly. So it's smaller also because the hum is less than the primary
Right.
noise. Yeah.
Otherwise, it would be inducing more hum.
Right. And so this lets them get away with smaller capacitors, or conversely makes the hum less for the capacitors they're using.
Who knew?
I don't think I've ever seen it in anything but a Zenith, actually.
Who knew you would learn so much tonight, right?
Right? This is great.
What I can't figure out is the value on the snubbers. I actually saw a radio recently that had a resistor in series with the capacitor, which kind of makes sense. If it happens a lot, you don't want to continue to stress the capacitor with high voltages, and so you can add it with the resistor. But I've seen values all the way from like 0.03 like that, all the way up to like down to 0.01, maybe. Not much more than 0.05, probably. But you think it would affect the output frequency, high frequencies? It'd start cutting off the high frequencies at some point.
Well-
Yeah, it definitely does. And that's what Atwater Kent uses it for, is to shape that top end.
Right. So it just sounds better.
Yeah, that's really, it's a tone control in that sense.
Yeah.
That particular capacitor is at about a 0.11 microfarad, 0.12 with
That's
power
pretty
factor
big. Yeah.
40%. So, kind of following the theme of what you carry over from what I've been working with before. This is the curve I've developed this week based on trying a different transformer in the output, or in that Atwater Kent. There are 2 transformers. There's an interstage and then there's the output. And the interstage, as you all know, Atwater Kent transformers are problematic. And certainly you find a lot of these guys in the bone pile because the first transformer is open. There's an open winding on it. So there's a cheap transformer that I've been touting is great to use, but I was wondering how badly it was actually coloring the sound. And so what you're seeing here is my effort to do the sweep generator thing. What I'm using here is my iPad running a a free app that you can get that does it's for like what do they call it? Real time analyzer. So it's doing it in third octave steps, but it does the sweep sound you talk about. It generates the sweep sound for you. And then I bring it back in. I tap off of the signal and bring it back into the microphone input, and I'm able to sweep the frequency response of this particular device. Now, you got to remember that in 1929, when this radio was built, we weren't talking about 20 kilocycles. We were talking about most of the radios of the era went from about 150 hertz to about 2500 hertz. That was considered to be the normal radio up until 1929. And they began to be able to push out the low end and the high end, and that was somewhat of what this was about. But the reason they didn't bother going any further was this is the circuit if you take it directly out, and where you're seeing this drop off is occurring at about 2500 hertz or 2500 cycles as you're seeing it drop off there. But if you put a reference microphone on that same device and look at the audio output,
Oh my gosh.
it changes it. You begin to appreciate how much that speaker is influencing their design choices. That speaker will hardly reproduce anything over about 3,000 cycles. And it drops off pretty rapidly at about 100 cycles on the low end. So it's really interesting to see the total impact of that exercise. But anyway, that's what was starting my process from last week when I brought up the conversation.
So what John is showing here, just in case not everyone is following, maybe everyone is, but if you're not following, what he's doing there is he's showing you the full spectrum that the thing should be running through. And ideally, I think you would like to see that flat all the way across, right?
Yes. Yes.
So in other words, if you put a certain input in, with dB being a ratio, you would really expect to see the output to be the same no matter what the frequency is. But what he was showing on that last chart was as the frequency increases, he was losing dB. So you were decreasing the amount of amplitude, which means that you're going to be rolling off your high end. All your trebles are going to be more muted, which is not going to make the sound as good as when it came in. Did I get that right, John?
You absolutely did. And that's just a word of warning too. Don't expect your 1929 radio to sound like a modern radio.
Yeah.
Right? They are different birds, and you can't necessarily expect to have the fidelity out of a 1929 radio. It just wasn't, to begin with, it wasn't in the transmissions. They were pushing pretty hard to keep about a 5 kilocycle bandwidth between for the station, and then most people stayed well below that. So you didn't have the signals to begin with, but you're also coming out of the battery era and the horn radio or horn speaker era and mechanical speaker era when those didn't matter anyway.
Yeah, John and I were talking about this earlier. It's kind of amazing because it doesn't, I mean, I'm not that old, but it doesn't seem like it was that long ago. If you think about it, in the early 20s, I mean, this was really breaking technology, coming through regenerative systems up into, coming up with being able to introduce an IF and all these concepts, it was built on top of each other a little at a time. They slowly figured it out and fought patents with other people to try to expand, but it took a while to get there. And the same way with records, which the next presentation I'm going to talk about, we're going to talk a lot about phonograph records and the history and how that has changed, and where you really can't, just like what he said, you can't expect something old to sound as good as today because you can't even reproduce a lot of that stuff just due to the way it was made. So yeah, it's really fascinating seeing the changes. And what we're doing is we're reviving the incremental technology steps as it goes through history.
Well, it may have been okay. Was most of what was on the AM broadcasting band 29 and prior mostly just voice, mostly talk?
There were exceptions. They were starting to have musical programs. Atwater Kent had the Atwater Kent Hour, in which he had uh, musical performers come in on studio. Of course, it wasn't recorded back then, and uh, so there was the beginnings of that stuff was coming out. But in 29 is about the era when you start hearing about the golden voice and the voice coil type speakers that could actually reproduce the whole band in a better form. And
So something I don't know about, but I'm guessing also the microphones that they were trying to use for pickups were probably, not to the quality of being able to capture the whole band spectrum either.
correct. Yep.
I was going to mention that that graph you created using a microphone, the microphone's going to have a nonlinear response also. So
It
in that curve, the
that
microphone.
particular microphone happens to be a reference microphone. I
Ah,
use it when
okay.
I'm tuning bigger rooms for when we do musical presentations, and you find that how far the wall is away from you bouncing off and so on. You got
Yeah.
to tune the
Okay.
device for it. So that's my reference microphone for that purpose.
Yeah.
But you brought up a great point though that so much of the stuff that we're dealing with is not linear. You just can't take a 2 points and say, oh, I can extrapolate out what it should be at this frequency. That's not the case at all. Anybody else have any other questions or comments? Was it useful to anyone?
Oh yeah, definitely.
Can't wait to get that square wave generator working.
Oh yeah.
Now, John, you said you used to do this, right? You did some work where you were introducing square waves and looking at the outputs.
Yeah, transmission lines and some of that sort of thing for higher speeds, but then in the ultrasonic world also trying to determine whether or not we were able to pass the complete signal from one place to the other when we're trying to develop higher resolution measurement devices. So yeah.
Has anyone tried this on an amplifier? Um,
Square waves, yeah, a lot.
yeah, I recommend giving it a try. Especially if you've got just a simple phono input. Obviously, you're going to need a scope or something to take a look at the output, but it's pretty cool when you can move your tone controls and actually watch that square wave shift around.
Yep.
Maybe we should set that up at a demo for um, one of the meetings sometime.
Well, that'd be really cool. Yeah.
Don't phono inputs have that RIAA filtering to it or amplification? So just a regular audio may not come through straight, flat.
That was to you, Mike. He's asking about RIAA compensation.
Oh, what was the question? I didn't get it all.
I was saying if you're putting audio into a phono input, it may have RIA filtering or the inverse of the filtering, I guess.
Yes. Actually, the next presentation I do, we'll go into that, and I'll even show you how to do the inverse RIAA equalization, so that you can test it. You basically put in a bad waveform, based on the RIAA curve, and then you should be able to see the square wave on the output.
But for the stuff you were talking about tonight, the easiest thing to do is just to come into the aux input or something like that, that's flat.
You might find it interesting on this Atwater Kent. What I ended up doing is pulling the detector tube and went straight into the plate circuit. Now you got high voltage there, but as long as you go in with the big enough cap, you don't have to worry about it feeding back into the rest of your device. It's fairly high impedance area, so you can feed it with a low impedance input. And but that was the way I was getting these signals out, was by literally unplugging it, putting a banana plug in the plate pin of the where the tube was, and injecting the audio tone there.
I'm sharing here. We were talking about the RIA curve, so I just thought I'd show what it looks like if you're not familiar with it. So you would have your recording. What they do is they actually screw up the recording, and they will lower the bass down here at 20 hertz, and then they'll increase the treble. We'll talk all about this, but this is what like a record is going to be outputting, and it should be straight across here, but that's what they actually do. They actually modify the sound going on the record. And so what the circuitry has to do in the preamp is it actually has to reverse this. So it has to take whatever the output from the record is, and then boost the bass, and then slowly degrade it down. And then when they get to the treble, they want to decrease the treble, so that when you get done, you have a flat curve. That's what they were talking about with the RIA equalization curve. But that's for another night. Yeah, in researching that, I found that really interesting. That record labels and stuff had their own curves for the longest time. So there was really no way to actually reproduce it unless you were doing it on the right, if it was a Decca, you needed to make sure that you were using something that would make sense to them, because they wanted their records to sound a certain way. Well, I don't have anything else. Jake, I'll turn it back over to you. Thanks, everyone. Awesome.
Yeah, thanks, Mike.
Thanks, Mike.
Yeah, I don't really have anything else for tonight other than as Pat had just recently emailed out, we are looking for a new call letter editor. So if anybody wants to jump at the chance, we would love to have a replacement sometime pretty soon. Because the last one Dick Carmen is doing is March. Last I checked, it is March. So we'll need a replacement here soon. Um,
Yeah, it's gonna be tough because Dick Carmen always prepared weeks and weeks in advance, so
mhm.
we should be working on April right now, but I don't know who can do this, or who has the skills and time to do it.
Yeah. But anyway, that's all I had for this evening.
Okay, well, I guess I'll sign off then.
All right.
Thanks, everyone.
Well, thanks
Yep.
again,
Thank you
Mike.
guys.
Good night, everybody.
Learned a lot tonight. Thanks.
Thanks for your
Oh,
help, John.
Oh, by the way, we've got lots of new radio books coming in. That was a donation. If you weren't at the auction, Susan Reinhardt with her stuff that she donated to the club, donated
Mhm.
like 35 radio books and like 10 pamphlets. So that's all going to go to libraries. So I really liked it because I saw a lot of books that must be out of print because I've never seen them before.
Hmm. Cool.
So I'll bring them in March for Dan and Jeff to take in the library. But you know, if you can see them, there might be stuff you want to check out.
Yeah.
Already
Cool.
got.
Well,
Have a good.
have a good evening.